Okay, so the last time we talked about this idea of monotone equations, which satisfy this kind of monotonicity condition. And then the net effect, if you will, is that if you have this property, then the time rate of change of the norm of the distance between two solutions of the differential equation is not increasing. Okay, so let's consider what the analog of this under discretization. So under discretization, the analog of the sort of norm increasing property, of course, would be that if you have u at, say, time step n plus 1 minus v at time step n plus 1, this is less than equal to un minus vn, right? So that's the kind of condition which you're hoping for, all right? And you can ask, well, under what conditions on, say, a Runge-Kutta method, are you guaranteed that if you were to apply the Runge-Kutta method to a differential equation satisfying the monotonicity condition, that you have this property that the norm of the difference of solutions sort of decreases or doesn't increase over time? Okay. So it turns out that it's like the relevant condition on Runge-Kutta methods is related to a particular matrix, right? So this is referred to as the famous matrix M, right? If you will, which is given as following: MKL is equal to BK AKL minus BLALK minus BKBL. Okay, where of course the A's and B's are the sort of coefficients, it's like of the Runge-Kutta method. Okay, all right, and then you can check that this sort of matrix is symmetric, right? So this matrix is symmetric. Okay. All right, so let me state a theorem now, which is a condition which guarantees that, again, if you have a Runge-Kutta method satisfying this condition, it's like, and you applied it to a differential equation satisfying this monotonicity condition, then what you will show is that the numerical solution satisfies this property here. Okay, all right, so if the matrix M, okay, which whose coefficients are given by this, right, is positive semi-definite, and weights B1 to Bs, right, are non-negative, then we say that the Runge-Kutta method associated that is algebraically stable, which is to say, again, that if you applied the method to a vector field satisfying this property, it has this sort of monotonicity property. Right, so that's again quite a reasonable kind of thing to aim for, right? That if you, so as we saw before, if you have a differential equation satisfying this monotonicity condition, then it's like the norm or the difference between two solutions is going to decay, or at least not increase over time. So you'd like a numerical method, it's like to have that same kind of property when applied to a vector field satisfying this condition. And the analog of that property, of course, is this inequality here. All right, and if the method does indeed do that, then we say it's algebraically stable. Okay, and the theorem is basically saying that if this famous matrix M, right, is positive semi-definite, then this Runge-Kutta method is going to be algebraically stable. All right, so let's try to prove this. Okay. So let's look at a single step of this method. It's like, so we consider a single step applied to two different conditions, right? Un and Vn, right? Okay, and then we see what happens. Okay, so big U J, right, is equal to Un plus H, the sum, well, let's write that Ui, right, sum over J of Aij Rj. And then R of j is just f evaluated at Tn plus Cjh, then Uj. All right, and then you have big V of I is Vn plus H sum Aij Sj, and then Sj is f evaluated at Tn plus Cjh, right, Vj. Okay. All right, and then, so I'm just writing down, it's like the definition of a Runge-Kutta method right now. I'm going to leave this monotonicity condition there, just to remind you what it is. Okay. And then I'm going to come back to this. All right. And then, of course, Un plus 1 is just Un plus H sum of B I Ui. Sorry, not U, Ri. Right, and then Vn plus 1 is, well, Vn plus H sum Bi Si. Okay, and you want to check that, so you want to show that the Un plus 1 minus U, well, back, Vn plus 1 squared minus Un minus Vn squared is less than or equal to 0. Okay, so let's write down what that expression is, right? So Un plus 1 minus Vn plus 1 squared is nothing more than the inner product between, it's like the difference of these two things, right? So that's Un minus Vn plus H, the sum from I equals 1 to S of, let's see, Ri minus Si, comma, Un minus Vn plus H, the sum over I equals 1 to S of Ri minus Si. Okay. So I'm going to denote this difference by d. Okay, so this is equal to un minus vn plus h sum. Oh, I'm sorry, there's a coefficient here, right? So bi, bi, bi. Okay, di un minus vn plus h sum bi di. So I'm suppressing the indices of the sum. Okay, so di is just ri minus si. Okay, so all right, so this inner product of this, of course, is just the un minus vn squared term. Then there's a cross term, which is 2h real part of un minus vn, the sum of bi di. All right, so these are the cross terms. And then there's something which is of order h squared plus h squared, which is the norm of the sum of bi di squared. Okay. All right. So so you can take this to the other side, and then you have to show that the remaining thing here is less than or equal to 0. All right. So you want to show that 2h real part of un minus vn sum of bi di plus h squared sum of bi di squared is less than or equal to 0. Okay, and I can get rid of a factor of h. So that's just 2 times this, and then there's a h here. Okay. So what I'm going to do next then is I'm going to have to deal with this un vn. Okay, and what I'm going to do is I'm going to write un and vn. It's like rewrite it using using the definition. It's like of the internal stages, right? So I'm going to replace un by the following. All right. So this is going to be ui minus h, the sum of a I j rj and vn is going to be vi minus h sum of aij sj. Okay, and this is of course just coming from the internal stage equations. Okay, so the advantage of doing that, of course, is that now you've gotten rid of everything it's like which involves un and vn. You just have a whole bunch of things which depend on the defects. It's like and you know, it's like other things like that. Okay, so so when you do that, we're going to rewrite this, right? So the real part of un minus vn sum of bj dj, okay, is going to be equal to, okay, the sum over j of bj okay, so I've taken the bj out, all right. I'm taking the sum out, and I'm leaving the dj term, okay, and I'm writing this un minus vn in the appropriate way. So this is going to be right uj minus vj minus h, the sum over aji di dj. Okay, so this term here is what I'm calling un minus, is just un minus vn, and then this is the dj term. Okay, all right. All right, so where were we? Yep. Okay, so this is equal to the sum over j of bj, the real part, of uj minus vj paired with dj. And the reason why that's of interest is because dj, of course, is the difference of the vector fields. It's like evaluated uj and vj, right? So that's something which we have an inequality on. And then you're left with something which just involves minus h sum over j, sum over I of bj aji, real part of di dj. Okay. So, all right, so again here it's like we are going to use the monotonicity inequality. And we're also going to use a property about the non-negativity of the weights. Okay. Okay. So using monotonicity, using and the non-negativity of weights, right? So using sort of the monotonicity condition plus non-negativity of the weights. Right, and you need a non-negativity of the weights, of course, because you're multiplying this term, which you have control over, with this. So you still need to know the sign of the b's to say something about this sum. All right. So if you do that, then you know that the sum over j of bi, real part of uj minus vj dj, right, is equal to it's just the sum from j equals to 1 to s of bj, the real part of uj minus vj. And then this is just the f evaluated at tn plus cijh uj minus f evaluated at tn plus cijh vj, right? And this is less than or equal to 0. Okay. All right. Okay. So that means that you're just left with this other piece. Okay. So you can relate this to this. So this implies that the real part of un minus vn sum of bj dj, right? So I'm just, it's like giving you an estimate on this piece here, right? This part is less than or equal to 0. So you can get rid of that. It's like, and then you just have an inequality involving these two pieces. Okay, so it's less than or equal to minus h sum over j sum over I of bj a ji, the real part of di dj. Right? Okay. So yeah, so the fact that this is non-positive implies that this term here has to dominate this term, because they had an equality before with this non-positive term here. Okay. All right. So let's see now. Okay. So now I'm going to swap the indices. On the second piece, right? So this real part of un minus vn sum bj dj is less than or equal to minus h sum over I sum over j bi a ij, real part of di dj. Okay, all right. So what that means then is that we can go back to what we are trying to prove, which is that, so recall you wanted to show that 2 times the real part of un minus vn paired into bj dj plus h bj dj squared is less than or equal to 0, right? All right, and we have a relationship, it's like involving this piece, okay, which is in terms of this other thing, which is going to be easier to compare to this. All right, so that's where we're going. All right, so this thing, right, 2 real part un minus vn sum bj dj plus h sum bj dj squared, okay, is less than or equal to, okay, so I'm replacing this here with this term. Okay. And of course, this can be written out involving the inner products, okay, and these coefficients. All right, so this is going to be less than or equal to h sum over I sum over j bi bj, right, minus bj aji minus biaij multiplied into the real part of di dj. All right, so this sum over I and j bi bj, real part of di dj term, is of course nothing more than this sum of bi bj dj norm squared term. Okay, and then these two just come from these two pieces here. Okay, so when the dust settles, it's like this is, of course, the coefficients of that matrix, right? So this is equal to minus h, the sum over I, sum over j, mij, real part of di dj. Okay, so then, so this is true. Well, I mean, it's like the thing you wanted to show is true, right? So the condition, okay, so you want to show this. So condition star 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 is true, right, if the sum over I, sum over j, mij, real part of di dj, inner product of di dj is greater than or equal to 0 for all d1 to ds in CD. Right. Okay, and then this is of course where you use the fact or the assumption, if you will, that Mij is positive semi-definite. Okay. So M is positive semi-definite, right? Which means that it can be written as M equals to W lambda W transpose, where W is orthogonal and lambda is diagonal, with non-negative coefficients, right? Non-negative entries. Okay. So, all right. So that means that lambda k, which is just lambda kk, all right, is greater than or equal to 0. Okay, so Mij, of course, is nothing more than the sum over k of lambda k wi. Well, let me write it down. So sum over I, sum over j, sum over k, right? Lambda k wik wjk, real part. No, sorry. Right, so that's what Mij is, and then we want to substitute that into this expression. All right, so so the sum. What am I saying? Yeah, so Mij is this, right? Okay, and then the sum over I and j of Mij, the real part of the inner product between di and dj, right, is equal to the sum over I, j, and k of lambda k wik wjk, real part of di dj. Okay, and this is of course nothing more than the sum over k of lambda k, the real part. So what I can basically do, if you will, is I can put these coefficients into this inner product, right? So the inner product of sum I equals 1 to, well, I'm just going to put I, sum I, right, wik di, sum over j, wjk dj. Okay. But this, of course, these two are really just the same matrices, the same vectors. It's like with just a different choice of indexing, right? So this is equal to the sum over k of lambda k, the norm squared of wjk dj squared. Right? This is, of course, non-negative. This is non-negative, so the whole thing is non-negative. Okay, so this proves basically that, again, if you have a Runge-Kutta method with the property that this famous matrix M is positive semi-definite, then it will have the property that you apply this Runge-Kutta method to a differential equation satisfying this monotonicity condition, that the solution will have the property that the norm of the difference of the solution at the new time is less than or equal to the norm of the solutions at the older time, okay, or the difference of solutions at the older time. Okay, and then and that's of course this notion of algebraic stability. Okay, so this implies that the norm of uk plus, well, u n plus 1 minus v n plus 1 is less than equal to norm of un minus vn, right, which is the condition for algebraic stability. Okay. All right, so that's basically the proof of that. And this matrix M is going to show up. It's like in a variety of other contexts as well. But yeah, so let's just stop here for now.